Today we are going to look at a very pivotal aspect of AI in modern times. All this while we have been talking about LLMs generally. And LLMs, yes, they are the aspects or the parts of the AI that allow you to, let's say, delegate some of reasoning capabilities, right? They can manipulate the prompts, they can generate output which they can look at the context and they can give you answers. Now, just having LLMs as they are is not going to be enough to solve real world problems. And that is why when ChatGPT was released for the first time in 2022, sometime in November, October, November of 2022, you find that, yes, it was quite amazing. It did a lot of interesting things. But at the same time, there were a bit of limitations, a bit of challenges, things that people would have expected an intelligent entity, to be able to achieve, but ChatGPT couldn't do it. Of course, the first thing that most people realized or saw or noticed was the phenomenon that we now call hallucination, which is basically the fact that when you give LLM, sometimes it gives you answers that are not true. It tells lies, basically. But not just that it tells lies, but it does it with a higher amount of confidence. It might even tell you with so much confidence on information or on something that is wrong. So, a lot of companies, you can't use that kind of system in an enterprise environment. Of course, we want to use AI in enterprise, right? We want to be able to use it in companies that need AI to solve a lot of problems, which AI is quite capable of solving. But this particular limitation, along with a bunch of others, was in the way. So, of course, as usual, the researchers went to work to figure out how to solve some of these problems. And that is when we came to understand that a large language model just on its own can do a lot, but it still is not enough. So we have to build what I call scaffolding around large language models. And we have to build harnesses. We now call them harnesses around large language models. We have to build additional things that will ensure that these large language models kind of are within the constraint of the requirements or the needs of um, whatever application it is being put to use. So one of the solutions that people came up with is RAG, what we call RAG, Retrieval-Augmented Generation. So this week we are going to talk about RAGs, but we will start off with all of the elements, the pieces that make up the RAG. So it starts off with the embeddings, semantic search, vector databases, and much more. So we're going to talk about that. So today we'll start off by looking at an overview of RAG. RAG means Retrieval Augmented Generation. And then we will look at the things around RAG. We are going to talk about document ingestion, right? Chunking and ingestion, basically. Then we'll talk about embeddings. Embeddings are the things that really make a difference. We'll talk about vector databases, which are a specialized form of database that's used at the back end to store embeddings. Then we'll talk about different types of embedding, vector databases rather, and we'll see how we can use one or two of them. Then we will do a little bit of a simple RAG implementation with Python, plain Python without using any, um, without using LangChain, right? We will use basic SDKs, right? And then we'll now look at how LangChain comes into the picture in all of this, right? LangChain has a whole new, gamut of tools that it provides that allows you to do much better work, both for the entire pipeline of RAG, including the chunking, loading, text splitting, embedding, and then retrieval. So that's what we will look at today. So for this first part, or this week rather, for this first part, right, the overview. So effectively, when we say RAG, like I said, RAG means Retrieval-Augmented Generation. And if you look at those three words that make up that acronym, each of them has a very specific meaning. The first thing is retrieval. So what is retrieval? When we say retrieval, we are talking about retrieving context, contextual data. And the whole idea behind that is the fact that if you are using just an ordinary large language model, like I said, there are several limitations, of which I mentioned a few at the beginning. The first one is, yes, the large language models are trained on data, so they can actually give you back that data on the information that they were trained on. And a lot of them are trained on a large corpus of data from the internet. So they have a lot of knowledge, they have a lot of information that they can give to you. But there's this limitation called the knowledge cutoff limitation. The knowledge cutoff limitation refers to the fact that at the point that you have trained a large language model, you can only train it on the information or knowledge you have at that point in time. So basically, that means that you can only train it. If you train a model as at 2024, it only has information up to 2024. It doesn't have any information of what happens beyond 2024. So 2025, 26, and so on. So for example, a language model I trained up to 2023 will not know who the current president of the United States is, right? Because that information did not exist as at the time that that model was trained. As a matter of fact, yeah, you could say that there were election campaigns, and so all that information may also be available. It can reason about it, it can guess, right? But it doesn't definitely we have that information. So the knowledge of a large language model always is affected by the cutoff. Where was the time at which it was trained? A very good example practically of where this kind of situation has come up for me personally is if you are using a copilot, right, to help you write code that needs LangChain, for example, or any of these recent, libraries, you'll find that it will still give you examples based on older versions of LangChain. Version of LangChain before version 1. Version 1 of LangChain was released last year, sometime in September, October. So most models that have not been updated for 2025 or 2026 will only give you examples based on version 1. And if you actually ask for more recent information, um, well, unless they do some reasoning or they do some web search, some internet search, that is when they will find that, oh, there's a newer version of LangChain and they'll pull data on that. But what is in their what they have been trained on and what is in their native knowledge or memory, there is that native knowledge or memory, is still going to be old information. So that's the problem with just using, one of the problems with just using a large language model is a knowledge cutoff. The fact that the knowledge that they were trained on tends to be outdated, of course, over time. So there is a knowledge cutoff date. That's the first limitation. The second limitation is hallucinations, which I just mentioned. So a hallucination is a situation where the large language model is giving you wrong information with a high level of confidence. And it's telling you that it is very sure that this thing is correct, but it is wrong. And if you do not know that it is wrong, You assume it is correct because the way it is so confident about it, you just take it that, oh, okay, this thing is correct. And you can end up making decisions based on that. So this is a very dangerous phenomenon because it leads, once people have begun to have a certain measure of confidence in what the large language model gives out or tells you, then you do not really bother to double check anymore what it tells you. And so you end up sometimes getting wrong information and you propagate that wrong information. This is one of the biggest challenges with AI of today. So it is something that there has been a lot of different ways that people are looking at solving it, right? We'll talk about some of the solutions, but researchers have looked at how can large language models be trained to have this concept of confidence, confidence in the information it's giving out. It should be trained to know when it is sure of what it is saying and when it is not sure. Because the difference between a human being and an LLM, human beings sometimes say, the wrong things as well, right? Excluding the malicious intent of I'm just lying to you because I want to mislead you or deceive you. But there are situations where I may have the wrong information. But human beings also know when they're not sure of the information they have. So that's the main difference between human beings' uncertainty and an LLM's hallucination. The human being knows when they are not sure of something, right? But the LLM does not. So that's the second limitation. The third limitation is that, yes, these LLMs are preparing a lot of data, a lot of information, a lot of knowledge from the internet. But there's a certain set of data that nobody has access to. This is organizational data. These are private data that enterprises, companies own. And it's not open to the public. So it's not available for training large language models. So these large language models don't have this information natively, as part of their knowledge that they have been trained on. But and at the same time, these companies will not also release this information because it's proprietary. So they will not release it to you for you to train models on. It's a bad plan, right? Because I will not release um, you know, my private proprietary corporate data from my company just for you to use to train your model so that it can be useful. The model can be useful to me. So even when companies need such capability, they still will not release the information. So that is a second limitation. And there's even an additional nuance to that where companies even don't want to be careful which server or which country their information gets to. So there are even laws around that called export control laws and all kinds of you know data privacy laws. Um, there is intellectual property laws. There's a whole lot of different laws around that. So it's not easy for a large language model to access private organizational data. But if you want the large language model to be useful to private organizations, they have to have access to the data. So how do we do that? And then it's also difficult to update knowledge of large language models without retraining. The only way is to gather additional new data, update the data sets that you have been training that model on, and then, retrain that model with the new data or with the data that has been updated. So this is not practical in a lot of situations because that means you would have to have large teams of people whose job is just to keep training these models for specific purposes or updating models' knowledge for specific purposes. So we now have this new concept called RAG. And how does RAG solve this problem? So you go back to the concept of retrieval. Retrieval basically means you can give the language model additional information, additional context to reason about information it didn't have before, information that wasn't in its training data. You give it that additional information because the language model has evolved or has been trained to a point where it it doesn't you don't need to train it with additional data. You can just give it additional data and ask it to reason about that data and give you answers, and it can do that. So that makes it very powerful. You don't need to do additional training. Just show it more data and it can think about it. So what then you do is that additional data is basically context. So think of it like a system prompt or additional information that you would have added to the prompt, which it uses to reason about. So we come up with a concept of retrieval. Retrieval then is retrieve additional knowledge, retrieve additional information, right, that the LLM didn't originally have or wasn't originally trained on, and then give it to it as part of the context, as part of the prompt, right? And it will be able to reason around it and respond, give you a more meaningful response based on that. That is what the R in RAG means. Retrieve additional information and give it to the large language model as a prompt, as part of the prompt, right? So you solve the knowledge cutoff limitations by retrieving additional relevant documents beyond the point of the knowledge cutoff, or beyond the point of the knowledge cutoff. You solve hallucinations by ensuring that the relevant documents for the question you are asking, right, is available. Because hallucination happens when the language model is trying to generate a response way outside of the data distribution, what we call data distribution, basically the knowledge it was trained on. And you're now asking it a question that is way outside of the distribution of the knowledge that it was trained on. It will still have to give you answers, but the answers can go way off the mark. So how do you solve that? You give it additional knowledge that brings it back into distribution, right? Additional knowledge that gives it more context on what you actually want to ask. So you're kind of updating it. And so it is constrained to um, generate its response within that context that you give it, in addition to other things. So you can solve hallucination by giving it real data, real knowledge, real information, and ask it to come up with answers around that. So remember, a large language model is basically a highly efficient knowledge store. Not just highly efficient, not just a knowledge that has a lot of knowledge that it has been trained on, but it is also able to, you're also able to retrieve that knowledge using that natural language. So if you give it additional knowledge, it essentially augments the knowledge it has. That is why you have the second word there, augmented, right? When you take, when you retrieve from wherever the knowledge is stored, the new additional knowledge, the knowledge that is beyond the cutoff, or the knowledge that is in a private organization, right? You retrieve that from wherever it is stored. You use that knowledge to augment the native knowledge of the large language model. And then the large language model is now able to generate answers based on this retrieved evidence. So that's why it is called retrieval augmented generation. Basically, generation of answers or responses based on augmented knowledge or augmentation of its knowledge, which is retrieved from somewhere else, not from its training data or it's what it already has in store. So retrieval augmented generation RAG combines the information retrieval. So the system has to be able to retrieve the information, and then it combines that with the large language models to generate responses that are grounded in external knowledge. The responses have to be grounded in external knowledge. So what we mean by external knowledge is knowledge that is not in the training data set that was used to train that model. It's external to that data set. So typically, the pipeline or the process of how retrieval augmented generation works is that for you to have that knowledge, that additional external knowledge in a form, because the next question maybe you'll be asking is, if you have some organizations or you have a large amount of knowledge, are you going to load all of that into your context window? Remember, you are just sending this knowledge as part of your prompt. So are you just going to load all of that knowledge into the, so let's assume you have, a database or knowledge base that contains 5 million entries or 5 million characters or words or whatever. Are you going to take that 5 million and load it into the context window? And we know that context window is limited. These days, the highest models have context window of maybe 500,000, 200,000. There are some models really top of the line models that can have up to a million size context window. But most of the models that you use for your day-to-day stuff will probably be limited to 20,000. At most, 20,000 is this number of tokens in the context window that you would have available. So how would you load all of this knowledge into the large language model so that it will use it to retrieve what it needs to retrieve and tell you, right? Secondly, is that even efficient? It doesn't even make sense. Like, it's going to be slow, okay? It's going to be difficult. So the question then is, all right, we cannot do that. It's not possible. So what's the next plan? Let's use keywords, to extract the aspects of the knowledge that matter. But again, remember, this is about meaning, not just keywords. So we now have the two aspects of RAG that answer those questions. One, we have what we call chunking. So we'll talk about chunking. Chunking is when you take this large external knowledge base and you split into smaller chunks. That's why it's called chunking. You store them in smaller chunks, but you store them in such a way that they can be easily retrieved. That's why it's called retrieval-augmented. So you retrieve the chunks that matter to the conversation. You store them in those chunks. And then you use embeddings. Embeddings are able to figure out the meaning of each chunk, right? Remember, AI works with meaning. AI doesn't just work with, um, it's not just the the um, the words, right? It's not just syntactic, it's semantic. It's not just about the words or the similarities between the words. It's not just about grammar and syntax, but it's about meaning. So it's semantic. So all the chunks that have similar meaning or have are related to the same kind of concepts, right, would have to be pulled out for a particular question or prompt. So it's the embeddings that allow you to be able to group or to first of all extract or understand the meaning of each of these chunks and then group them, right? So, and then a vector database is effectively a database that is optimized to store embeddings. We'll talk about all of this. So the typical pipeline is So as I was saying, the process for RAG starts off with the documents. You have documents, large, amounts of documents that you want to use. And then you take those documents, you split them into chunks. So the chunks allow you to deal with smaller, manageable pieces. So if you are sending it to the large language model as part of the context window, as part of the prompt, you only need to send small chunks. Then the embeddings allow you to extract the meaning of each chunk so that when you are searching for the relevant chunks to send, the embeddings will guide in finding the ones that matter based on meaning, not based on syntax or similarity of words or anything like that, but in terms of the semantic meaning and semantic similarity. Then it is going to be stored in a vector database. Vector database is a database that is optimized to deal with vectors, embeddings. Embeddings are vectors. That's why they're called vector database. We'll talk about that shortly. Then a retriever. Retrievers are special elements in this context where LangChain introduces this concept of retrievers, which allows you to retrieve information when you are looking for specific things. And then the retriever will pull the chunks that are relevant to the prompt or query from a user, right? And then those relevant chunks are embedded into the prompt. So the prompt is going to be boosted by additional knowledge that is retrieved from the vector database, right? And then that boosted prompt is going to be sent to the large language model. And the large language model will then give you a response. So that's typically the entire pipeline, and we're going to look at each of those. So let's start with the first in that pipeline, which is the document ingestion. Document ingestion is the process of converting the raw data into a searchable knowledge base. And document ingestion, you ingest document from different sources. So whatever format the document is in, PDF documents, Word documents, websites, right? Wiki sites, databases, emails, you know, JSON or CSV files, SharePoint. But this is not even an exhaustive list because even slides, right? Presentations, drawings, there's a whole everything, any kind of document, right? And the goal of ingestion is number one, the meaning has to be preserved, right? So remember, in everything with AI, with large language models, we are dealing with meaning. So the meaning has to be preserved. The retrieval quality has to be high. We're going to talk about retrieval later. Retrieval is when a user is trying to get information and types in a prompt, being able to locate the chunks that matter, the chunks that will give the correct context or additional information or knowledge to the large language model for it to be able to generate the response, right? So retrieval quality matters in RAG. In fact, there are a lot of things that matter when you're talking about RAG, this entire pipeline. Then you want to minimize noise. Noise is when, if for some reason you are retrieving and you are bringing in data that may kind of sidetrack the large language model a bit, or data that doesn't even really matter, okay? Or results, chunks that don't really add additional information. You always want to be able to retrieve chunks that matter because there's also a constraint in retrieval. You cannot search infinitely and you cannot retrieve an infinite amount of chunks. You're always limited by resources. You're always limited by latency, by the response time that you want your users to perceive. So you're not going to have the you know the um, ability to just retrieve everything, right? So you have to be efficient. You have to apply some efficiency. Same thing applies with searching, right? You need to be able to search efficiently. We'll talk about search in RAG later on. So some of the challenges that you have when you are doing ingestion is you have a lot of large documents. And we'll talk about how large documents are a challenge. But the primary challenge with large documents is meaning that is separated, you know, by a large that are spatially or in terms of where they are located in the document, they are widely far apart, they're separated far apart. But so physically they are far apart in the document. Maybe one part of this information may be on page one, and the other part of the information may be on page, 50 or page 100. But those two parts are actually, you know, needed. They're part of the same information, right? And so from a meaning standpoint, they are close, but from a physical, or spatial position in the document, they are far apart. So that's a problem, uh, especially in large documents. But generally, ingesting large documents is always a challenge. Then the second challenge is tables and images, mainly because re ingestion and chunking always depends on the nature of words or paragraphs that are kind of sequential, right? But tables and images are not necessarily sequential in that way, right? Tables have a separate kind of structure. So ingestion needs to understand or recognize when it has met a table. You cannot chunk parts of a table, right? You have to take the whole table, and it has to still be a table. The relationships in a table are different from the relationships in a paragraph, for example, between the words in a paragraph and between the concepts in a table. So that poses a challenge. Images, the same thing. Then, of course, duplicate content. So duplicate content is also a problem. Inconsistent formatting in documents. And then, of course, frequent updates if your documents are getting frequently updated. So the typical ingestion pipeline is you have the raw document, you load the document. So there's what we call loaders. Um, you can already see that there are different formats for documents, right? So these formats are not the same. You're not going to use the same code base or library. You're not going to use the same method to load these documents. They are different. So loaders allow you to do that. Then after that, you still need to clean the loaded documents, remove um, you know, bad information, bad data, not information, but bad maybe encoding, um, excess space, all of that kind of stuff that doesn't really form part of the document itself. And even some kind of formats like websites have markup HTML, Markdown, and so on. So all of these are things that really matter. So you should be able to clean it a little bit before you now move on to the chunking phase. So chunking, like I said, is where you take the document as large as it is and begin to split it into smaller bits and pieces. Then embedding. Embedding is where you extract the meaning, and we'll talk about what that means when I say extract the meaning. Okay. After that, you store in a vector database. The vector database allows you to store a chunk side by side with the embedding. So you store the data side by side with what its meaning is. When you are running search, you are going to run search not on the content or the chunks, but on the meaning itself. Well, okay, you don't actually store the chunk. The chunk is stored depending. You could have a situation, but it's more efficient to store the chunk on the file system. right? Even though sometimes you could also store the chunk in the data store, right? But typically you are going to store embeddings, you're going to store metadata, but the chunks will be stored elsewhere. It's not efficient to store. It's just like saying you store the actual image in a database. In most situations, we don't store images in a database. We store the image somewhere on the file system, and then we store the URL to an image in the database. That's how you do images. So that's the same principle. The chunk will be stored somewhere, right, on a file storage, while the references to the chunks, which will be the embedding and the metadata, will be stored in the database. So that's typical document ingestion, and we'll look at it in more detail. So the first part of ingestion is chunking. So why do we need to do chunking? Um, Number one is the context limitation. In fact, that's the main thing, right? Like I said, most or if you have a really large document, you're not going to take the whole document and stuff it into the context window when you want to use it for retrieval, or when you want to use it for generation, rather. So you have to chunk. That's the main reason. You have to split it into smaller um, bits and pieces because of the context limitation of the large language model. Apart from large language model itself, which is doing the generation of your response, the embedding model is also going to create an embedding, which is essentially the meaning of that chunk of text. So embedding models also have um, context limitation. The context size of embedding models are far, far smaller than the context size of large language models. Embedding models are actually small models, right? Typically maybe 300 and something, 500 and something, sometimes 1,000. I think the largest I've seen is 2,000. But then these days, people may be making even larger embedding models. But there's also a downside to having embeddings that are very large in size. So a good example is if you have a 200-page manual that you want to store, right? A 200-page manual may have about 100,000 words. And typically, rule of thumb is the ratio of words to tokens is about 1.3. So tokens is always about 1.3 times, 1.3, 1.4 times the length of the number of words in any document or text or string. So if you have a 200-page manual that has maybe approximately 100,000 words in it, then you're looking at approximately 130,000 tokens. You cannot embed this. It's not possible, right? Well, maybe it's possible with a very large model, okay, but it's not efficient. It's not effective. So you cannot embed or retrieve this as one document. So the solution is the chunking that we talked about. So in chunking, you are going to split the large document into smaller, meaningful pieces. The benefit of it, like I said, is you have better semantic search because you are now searching on smaller chunks or smaller parts of the document, smaller sections of the document. Think of a chunk like you take a big document and you're splitting it in small sections, right? It reduces the cost of embedding. So the cost of embedding is not just a cost in terms of dollars or naira and kobo or whatever, but in terms of the time, performance time, speed to do embed as part of your ingestion pipeline, right? So embedding costs will be reduced because you're dealing with smaller chunks. Faster retrieval, you retrieve faster because your embeddings are also going to be smaller, right? The size of the embedding vector is going to be smaller, so you can retrieve faster. And the chunks are also smaller, so you can retrieve faster. You have more precise context. Where this matters is you are only pulling the pieces of the document that matter to the question that you are trying to answer or the response you're trying to generate. So you're going to have a more precise context rather than taking a whole document that may contain a lot of other things that don't really matter or not relevant to the prompt or the question that the user is asking. Then you have an improved answer quality. Of course, you have an improved answer quality when you have a better context, right? So the large language model doesn't hallucinate and go in the wrong direction. If you have a language model, a large language model that doesn't have an answer, and you're using the retrieved document to give it context, then the context needs to be very precise and very relevant to the prompt. Because if you give it other stuff, it can still go in that direction and get lost, giving you responses that do not matter. Okay. So, um, that is um the benefit. Now, a good example of, well, we have poor chunking and good chunking, right? If you were to do this kind of chunking where you have a document that is explaining installation process, and then you are now splitting a sentence into two pieces, right? This is not good chunking because you have one chunk that is made up of half of the sentence, the installation process. Then you have a second chunk, chunk two, that is made up of the remaining half of the sentence, requires configuring this. So this is not a good example of chunking, of good chunking, or this is an example of bad chunking, right? The main problem with this, of course, that the meaning of this particular sentence has been split across multiple chunks. So you typically always want to keep your chunking meaningful, right? Your chunks should have meaning of themselves. Okay. So there are multiple different approaches that we use for chunking. Okay, we have fixed size chunking. Fixed size chunking is where you specify the size of a chunk, right? So you could say, okay, chunk size should not be more than 500 tokens. So when you take a large document, you split it into chunks of 500 tokens each. There's typically what we call overlap. So overlap is additional tokens that you can overlap, right, above that um, chunk size. The benefit of overlap is then that um, you don't cut off meaning abruptly between the two chunks, right? Especially if the chunk contains, at least you are sure that you can get a complete sentence before the end of that chunk when you apply an overlap. And then the chunk that follows it, which continues from the end of this chunk will overlap backwards also by the same 50 token overlap so that you will have meaning that is retained somehow between the two chunks. You don't lose meaning. So that's the benefit of overlap, right? The advantage of using fixed size chunking is very simple to implement, right? You just run through the document, and after 100 plus the overlap, you stop. You end the chunk there. You save that chunk, and then you move to the next one, right? That's the benefit. It's very simple to implement from a coding standpoint, and it runs very simply. It's also very fast because there's not much, analysis of the document that needs to be done. You don't even do any analysis of document. You just split it. But the disadvantage that it has is that there is no actual knowledge about the structure of the document. And this fixed size chunking doesn't even care about the structure of documents. So you're going to end up splitting sentences in the middle, especially long sentences, especially if you have a sentence that is longer than your overlap, right? You still end up splitting that sentence. Okay. So it also breaks semantic meaning because it does not look at the meaning of the entire thing, right? So it doesn't even care when the meaning is broken, right? Or it doesn't care where in the middle of the sentence or paragraph or whatever it is, or data or the structure, it doesn't care where it is broken up. So that's the disadvantage of fixed size chunking. So there are situations where fixed size chunking is good, but there are also situations where it's not the best strategy to use. Then the second type of chunking is what we call recursive chunking. So in the recursive chunking, the approach is it looks at the document structure. And the structure it looks at, it starts with the largest document structure, which is a paragraph. And then it looks at the next largest document structure, which is the sentence. And then it looks at the um, lowest document structure, which is the word. Most tokens correspond to words, so it cannot go below words. It cannot go to like letters or anything like that. So the way it works is that it first of all starts by attempting to chunk the paragraph. So it looks for the boundaries of a paragraph, beginning and end. And typically it tries to fit that paragraph into, even in recursive chunking, there is still a maximum token size. There's a token limit. So you are still not chunking it, without constraint or without boundaries. So it will still try to see if you can get the whole paragraph into one chunk. But if the paragraph is too large to fit into one chunk, then it will go down to the next smaller unit, of the document structure. Look for how to fit a sentence into one chunk. If it succeeds, then it ends there and goes to the next chunk. But it fails, then it tries to go to the next level, which is trying to fit a word into the chunk. Of course, words will always fit into the chunk. So it always does that iteratively. The advantage of recursive chunking is that it preserves the context because it's looking at the structural nature or form of the document that it is trying to chunk. So it's the most commonly used because of that, because it preserves that context. Then we have a third one, which we call semantic chunking. So with semantic chunking, the idea is to split based on meaning rather than size. So in semantic chunking, the length of documents, or sorry, the context size is not really a constraint anymore, right? Even though there's still a max, there's always a max limit because without a max limit, you could end up just pulling in the entire document as a single chunk, which defeats the whole idea of chunking. But the idea is to look at meaning, right? So instead of saying, let's split based on every XYZ characters, right? We look at meaning and we try to understand where the meaning changes. Then you move into a new chunk where the meaning, the piece of the document that has similar meaning or contributes to the same meaning will be pulled into one chunk, right? So the advantage of this is because you are focusing just on the meaning. So you are chunking based on meaningful parts of the document, parts of the document that contribute into the same meaning, right? Or into the same concept are pulled into one chunk. And after that, the next part is also pulled into one chunk. So it will give you high retrieval quality because it means that whenever you pull chunks out, they are complete in terms of the meaning that they carry. However, the disadvantage of it is definitely more computationally expensive because for you to get the meaning, it means you have to do some kind of embedding as well. So you have to do a pre-embedding, essentially look at paragraphs, sentences, and so on, and see how you can compare meanings of those. So there's a bit of embedding there. So it's very computationally expensive. This would be an approach that you would use for high profile documents, right? Especially documents that, for example, legal documents or research documents where you don't want to lose meaning. The meaning matters. So yeah, but in each case, there is always a trade-off. So there's always a decision to be made of which approach do we use or not? Okay. Now, when we're talking about the basic chunk, there's a chunk overlap. In most cases, the chunk overlap is used. Chunk overlap is very important because it allows you to capture information that maybe somehow the entire chunk normally would not have captured it, right? Important information always tends to cross chunk boundaries, no matter which approach you use. So when you have a little bit of overlap, it means that you can capture the meaning into the previous chunk and also capture the meaning into the next chunk. Because this is a good example. Um, if you just did a simple length-based chunking or size-based chunking, right? Or fixed size chunking, you would have a situation where you could have a sentence like this that is split into two, and then you lose meaning, right? When you embed this first sentence, the, sorry, this first section of the sentence, the meaning is actually quite different from the entire sentence itself. Same thing with if you embed the second part, the meaning is also quite different from the entire sentence. So you lose meaning by splitting the sentence into two, right? Now, but with overlap, you have a situation where the first chunk still has a little bit of the second chunk in it, right? It still has a little bit of the second chunk in it. So that allows you to preserve the meaning. That's mainly because if you look at this, chunk one is still cut off at this point, right? But chunk two goes backwards. So unlike here where it basically just chops it off, but chunk two, the overlap allows it to get a piece of the chunk one as part of chunk two. And that piece of chunk one that um, is added to chunk two enhances and preserves the meaning. And typically there is um, some kind of correlation between the size of the chunk and what you would use as overlap. So it's typically between 10, 10 to 15, 20% of the chunk size. So, but when your chunk size becomes bigger, you can afford to do more overlap, right? So that's a rule of thumb. Overlap is typically 10 to 15, 20% of the chunk size. Now, apart from that, there are other advanced methods that you would use for chunking. We have the structure-aware chunking, where you look at a document structure. This is very useful for Markdown and for HTML, right? Where you're looking at document structure, if it has headings, sections, it has bulleted lists and tables, right? So this allows you to maintain the hierarchy or to preserve the hierarchy of the document. This is actually very important for web documents, Markdown documents, and other kinds of documents that have a specific markup language. Then we have a parent-child chunking, right? So this one, the approach is that you are storing, for retrieval purposes, you store small child chunks, and then when you want to create context, then you can pull a parent chunk and bring in the child chunks. So in storage, there's actually references that are created, right, to link the chunks that are child chunks with chunks that are parent chunks. In fact, this is kind of the best approach. So the example here would be is what we call page-based chunking. So in this case, you're always chunking pages or multiple pages. But when you chunk the pages, you are not um, taking the whole page and all its content, because that would be a bit, that would be kind of duplication. what happens is you take paragraphs in a page as chunks, for example, and then when you take the paragraphs in the page as chunks, then you take the whole page as a chunk. But you are not storing the page itself. You are rather using the page and you are referencing each of the paragraphs, which are children chunks of the parent chunk. So that's why you have this kind of hierarchical structure where the parent chunk is still stored, but it's not the content, right? The parent chunk and the meaning, the embedding of the entire page is stored, right? But in terms of the document itself, the metadata, right? It's only referencing which other chunks are inside that page, right? So this allows you to maintain meaning of the entire page without having to store the entire page or retrieve the entire page. Okay, so this is quite efficient, and this is what is used by a lot of enterprise RAG systems. There are a whole bunch of other different chunking methods that we use as well. One other thing is when you chunk, you can also attach metadata. So this helps when you are doing filtering and when you are doing citations. So we are going to see a lot of these examples. Best practices for chunking. Um, Number one, preserve semantic meaning. So if you're writing chunking code, always try to preserve the meaning. Don't split in the middle of paragraphs. Try to split at section boundaries, right? At the beginning and end of a paragraph. So the whole paragraph becomes a chunk. And if the paragraph is too large to fit into the max chunk size, then you can go down to sentence in the paragraph. So maybe the paragraph has like 3 or 4 or 5 sentences. If you then take out one sentence or 2 sentences, you can take out 2 sentences from that paragraph, right? And use that to make up one chunk. Then the remaining three, use it to make up another chunk. The second is maintain consistent chunk sizes, right? When we say consistent, it's plus or minus within a range. It doesn't mean that they will all be exactly the same size, unless you're using fixed size chunking, right? If you're using fixed size chunking, then of course, but even with fixed size chunking, there is overlap. But most of the other methods that you see here, you are going to have an average chunk size. So chunk sizes should be within that range. So maybe if you say my chunk size is 500, you may have some chunks that are 550, 600, others maybe 490, and so on. But you should not have a situation where you have this kind of variance, where you have a chunk that is 50 tokens and another chunk that is 5,000 tokens. You can see the size difference is too much. It makes it very difficult to manage retrieval, managing your context, managing your you know, the context window, doing calculations on how you manage context window and things like that. Yeah, the other guideline that is recommended is include metadata. So use those fields from the original document that you will add when you're saving the chunk. Include things like the source, which is the name of document and all of that, ISB and all of that, the page number where that chunk came from, the author of the document, the date, the section title, and things like that. Then, when you are doing retrieval, always check and measure retrieval quality. We're going to talk about this when we go to retrieval, right? Some of the metrics that you look at is recall, precision, relevance score, and answer accuracy. We are going to look at these metrics later on when we're talking about evals, especially evaluation of the RAG system. Okay, so let's talk about embeddings. What are embeddings? Embeddings are simply a numerical representation of meaning. That's what an embedding is. Embedding is just a number, or rather, it's a list of numbers, a list of floating point numbers. You can see example here. Because remember, the large language models, these are neural networks. Neural networks only deal with numbers. all of the words that we send to these large language models are converted into a number format. And how they are converted is using embeddings. So an embedding is a multidimensional, um, vector, basically a vector that has, um, a vector is an, an array or a list. So from a programmer standpoint, when you hear vector, right, it's basically a list. From a mathematical standpoint, a vector is, yeah, think of it that way. It's a sequence of numbers. It's a list, right? This is different from the vector from a physics standpoint, which is still a sequence of numbers, just that it's two numbers. One number determines the magnitude and the other one determines the direction, right? Or you can split it into the components. So if you actually look at it from standpoint of physics, the vector can be reduced or resolved rather into its components. And if you are resolving in a two-dimensional space, you're going to have two components, the x value and the y value, right? Those two values form a list of numbers, right? That is what basically the length in the x along the x-axis and the length along the y-axis. So in a two-dimensional vector, that's in a three-dimensional vector, you now have three numbers, right? X, Y, Z axis, the values of that vector on each of those axes, right? So now extend that reasoning to a multidimensional space. That's what is happening because when we talk about neural networks, machine learning, and so on, we're talking about multidimensional spaces, right? So in a multidimensional space, this embedding or vector is basically numbers that represent the length in each of the axes in a multidimensional space. So you could be talking about 200, 300, axes. Okay. And so you have 0.21. So for example, this is just an example. This might not be what it is, but effectively it reduces to just a list of floating point numbers, a list of numbers that can be either positive or negative that represent this word. Every word has a different list of numbers. So if any particular word has these two numbers the same, that means it's the same word. In fact, it's the same meaning. The thing is, these numbers represent the meaning of the word, right? And so two words that are similar or close in meaning will have vectors that are similar or close. But the question now is what metric are we using to measure the similarity or closeness, right? And that's where if you go back to the first principles, how do you calculate the closeness of two vectors? They should face the same direction and they have a similar magnitude, right? To calculate the direction, you will use in a two-dimensional space, you use Pythagoras theorem. But I'm not going to go into maths because it's not machine learning class. This is AI. So effectively, there are methods to calculate the similarity in meaning, which is basically if those two vectors are facing the same direction or the directions that they are facing are similar. So there's what we call embedding space. The embedding space is a place, think of it, visualize it as a multi-dimensional space where when you plot these numbers in that space, 2 points in that space that are close in meaning will be close, together in that space. And 2 points that are opposite in meaning will be far apart, right? And all of that. So this is a topic that is quite interesting and I would recommend everyone to go into it. But from the standpoint of a programmer, a developer, right? An embedding is just a vector of numbers, but these numbers have meaning. So for example, this would numbers will represent the meaning of the word dog, right? These numbers would represent the meaning of the word puppy. And when we say meaning, meaning as learned by the large language model or the embedding model that was trained on it, basically the neural network that was trained on it, right? So these numbers may not be the same if you are using two different embedding models. They will not be the same because even if they are trained on exactly the same data set, They will not learn the same embeddings the same way. So this is something that we need to be you need to take note of. So embeddings are basically the numerical representations of meaning. So anything that you give into an embedding model, whether it's text, image, or any data, it converts into a dense vector. A vector is, like I said, just an array of numbers, right? Even though the actual meaning is it is the component of a resolved vector in a multi-dimensional space. But that's physics, that's a math. So I'm not going to go into that. So when vectors are have similar meaning, they are close, right? And they point in a similar direction. But when vectors have different meaning, they are far apart in that embedding space, right? And they will point in opposite directions. If you calculate direction as a measure of well, let me not go into that. So why do we have to use embeddings? Because when it comes to AI, it is meaning that matters. It is the semantics that matter, right? Not just the keywords. Similarity is not about whether the words are similar. For example, car and card. If you have car and card, those two words would mean the same thing, or sorry, are similar, right? From a syntactic or spelling standpoint. But car and cards, right? But are they similar in meaning? They're not similar in meaning. So you cannot just use standard keywords correlation or closeness of keywords. In fact, in the past, there were different methods we used to try to see to figure out how close words are in terms of meaning. There's what we call Levenstein distance. I've actually used that principle, to calculate. Levenstein distance is a measure of how many transformations you make to each letter or character in a word for it to become another word, right? So that uh, how many characters you would flip, right? So for example, Levenstein distance between car and card is 1. Flipping also includes changing the letter or adding a new letter. So for me to get from car to card, I'll need to only add one new letter, right? So Levenstein distance of car to card is 1. The Levenstein distance of care to card is also 1. So if you look at care, for example, care to card, the Levenstein distance is 1 because I only need to change one letter, right, for me to convert care to card. So if I was using Levenstein distance as a metric to measure similarity, these two would have the same score. But this other one, right, car to automobile, you can see that Levenstein distance here is a lot, right? Because I would have to remove C, okay? So that's one operation. I'll change the R to U. That will be 2 operations. So I now have AU. Then I need to add all these other ones, which is 1, 2, 3, 4, 5, 6, 7, 8. So that's a total of 10 operations for me to transform car to automobile. So the Levenstein distance here is 10. So if I was using Levenstein distance would tell me that car card is closer to car than automobile, right? So I would pick card, but that's the wrong choice because semantically, card and car are very far away. They are totally in different domains. But car and automobile are the same, similar. Embeddings would tell me that car to automobile will give me a higher score, but Levenstein will give me a lower score, right? For car to automobile, the comparison of those two. So this is where the power of embeddings come in the context of in the context of AI, right? In the context of intelligence, in the context of large language models. Because what you are focused on is knowledge or meaning, not not um, grammar, right? Not keywords, not how close these are. So this is why embeddings are very important. And in AI today, right, semantics matter, right? So it is very important, the semantics. If you are not able to establish the clear semantics, right? Semantic um correlation between two things, you will not exhibit intelligence, right? Your application will not exhibit intelligence. So embeddings become the most important metric right now. So embeddings are typically used in a lot of places. You can even find that embeddings are used in search engines, right? Semantic similarity, like what we said, recommendation systems. You can actually build a recommendation system just by using embeddings and comparing embeddings. So how do you use embeddings in a recommendation system or recommender systems? A good example is if if you have an e-commerce site, for example, and people come in to make purchases, all you need to do is embed their purchases, right? Um, I'm buying, for example, t-shirts on a site. Somebody's buying shirts. Um, Others are buying socks. Then some people are buying bed sheets. Others are buying nail polish and things like that. By the time you apply embeddings, you find that the things that are similar will be in the same space, right? This image is a good example of it, right? But things that are different will be far apart. So you can then calculate the semantic distance between two things, right? And then you can figure out that, oh, okay, these are similar. So you can then say, um, if this person bought this similar stuff, or if this person bought this thing, then these are the other similar stuff that this person can also buy. And then you can bring up a part of your website that says, okay, also check this out. If you bought t-shirts, also check out maybe um shirts as well. That's one way. Another way is looking at what users are doing. So if you gather the um history of purchases of a particular user and use that and make an embedding of that, then you find that users that make similar purchases would have embeddings. If you get their history, the embedding of that information would be similar for those who make similar purchases. And then you can find users that are similar in that way and find other purchases that they make that this particular user has not yet made. And you can say, okay, users that made what you bought, that bought what you bought, also bought this other kind of stuff. So that's recommender. Then clustering is essentially grouping things, being able to classify or group things or categorize things, right, based on similar features, even when you don't know what those similar features are, right? Embeddings allow you to do that. And the way you do that is basically if all the embeddings are close together in the same space, then they are similar, right? Of course, RAG, like we've talked about, and classification. So, by the way, this slide came from a machine learning thing. So that's why it seems like it's more of a machine learning thing. There's an interesting um, visualization of embeddings, which I would like to just allow us to see. So it gives you a mental, um, idea of it. If you look at this, you see that words that have similar meanings are close together. Decision loss. Words that are far apart, right, have different meanings. But you always see that the words that are close together tend to have either similar meanings or in the same domain, right? So this is how embeddings work. Let's take a quick look at this projector. I hope it is still there. I always find it quite interesting. It takes a bit of time to load. So I'll let it load. When it's done loading, we'll come back to it. All right. So how do embeddings work? So the first thing is tokenization, right? This is kind of going a bit into the things that make an embedding. So remember I said embedding is a sequence of numbers, which you will see it as a list of numbers. And the dimensions are typically between 384 to 1536. Um, so 384, and a vector of dimension 384 will have 384 of these numbers in the list. Basically, that's the length of this list or array. In other words, there are 384 dimensions where that vector has been resolved. Okay. Now, the first step is for you to get to the point where you are getting these numbers, you first of all break the numbers, the words rather, the words in the text, you break it into tokens, right? A token, effectively, you can think of it as a word. So you are breaking the text, the whole sentence or paragraph or whatever into words. Okay. So this is a good example, right? You break it. Now, these days, the neural networks that we use for embedding actually sometimes they break uh, the text into sub words, right? They may not be full words, but they may be half of a word or a piece of a word, right? Um, in those days, in the early days before uh, large language models, embedding models, and so on, people used to just use words, right? But machine learning has advanced to a stage that now embeddings are not generated by people, but are generated by the language models, what we call embedding models. We are going to see a few of them shortly. Okay, so you take the words, you take the text, right? It could be a sentence, it could be a paragraph or whatever, you split it into words. So you now have a list of the words, right? Then you take these words, okay? Each word will be then passed into a pre-trained neural network model, which we call the embedding model, right? It will now convert each token into a numeric vector. So this first token, for example, artificial, you get a 384 length array or vector coming out to represent artificial. You have another 384 length that represents intelligence. You have another 384 length that represents ease. Another 384 length that represents amazing, right? So each of these vectors represent the entire meaning. It captures the context, the meaning, and the relationships between this. So it is this vector that you are going to store in the vector database. That's why the database is called a vector database. The vector that represents meaning is called an embedding. So when you now want to compare vectors, there are different ways of calculating it, right? Right now, there are three ways that you have here, but there are a bunch of others. The first one uses what we call a cosine similarity. Cosine similarity basically uses there are algorithms for it. It's a simple mathematical formula because again, these are just mathematics, right? As the name implies, it actually uses a cosine because it measures the angle, the angular distance between the two embeddings from a particular point in that multidimensional space. So that's one way. The other one is a Euclidean distance. Euclidean distance, for those of us who have done a little bit of maths, when you reduce a Euclidean distance into a two-dimensional space, it corresponds basically to the Pythagoras theorem, which is c squared equals a squared plus b squared, right? So, um, but in a multi-dimensional space, it's kind of the same formula, right? Um, it was di- discovered by Euclid, who is, who is actually a famous mathematician. So that is the second way. Then the third way is a dot product, right? Um, is a dot product. So um, these are the three ways of calculating similarity. Basically, it's calculating distance between the two vectors in the multidimensional space. That multidimensional space is represented again this way. We are going to see it when we get to this embedding protector. When you're using cosine similarity, if you have a value of 1, it means that those two vectors are very similar, very close to each other, right? If you have a value of 0, it means that they are not close, they are not related in any way, right? There's no correlation between those two vectors. If you have a value of -1, it means that they are correlated, but in the opposite direction, in the opposite manner. They are highly correlated, but it's a negative correlation. So what that means effectively is that those two words are almost opposites of each other, right? That's how um, so for you to be able to get embeddings, you use embedding models, and we are going to try a few right now. Just call a model, right? Send it a word, and it will give you back an embedding. That's how embedding models work. And we're going to do a few of them now, with simple API calls, right? There are a bunch of them. I think probably some of these, you have text embedding, three small, three large, and you have open source models. If you go to Hugging Face, you see a lot of embedding models on Hugging Face, right? But when you are choosing the models you want to use, remember you are going to choose for accuracy, you're going to choose for latency, which is response time, for cost, for the vector dimension, right? And language support. Language support is very important because a language, an embedding model that has been trained on multiple languages, on data from multiple languages, will be able to create embedding in different languages. And two words that mean the same thing but are in two different languages will have similar embedding that the cosine similarity would be very high. So you know that they are correlated. So if you are trying to, if what you are building has to do with language, like language translation app or something like that, ensure that you are checking the language support of the embedding model that you are using. So these are examples of how you can do embeddings if you are using the native SDK. So you can use the OpenAI client, and you use client.embeddings.create to create an embedding. Of course, you first of all you get an embedding model, and then you pass in the text. You are going to get an embedding. This embedding is going to be a list of lists, a list of vectors. Remember, each word comes out as a separate embedding vector. Hugging Face also has sentence transformers that you can use. And then this all mini LM is also something you can use for embeddings, right? So we are going to look at how to do that. You can also do what we call batch generation, where you can pass in multiple words and it will actually generate embeddings for all of them, right? And then when you get embeddings, you can then store them in vector databases. So we're going to talk about vector databases when we come back um, next on Friday. But for now, I just want to do a little bit of hands-on. We've talked a lot about different things. We've talked about chunking. We've talked about embeddings, and I would like to just do a few things. This is a nice way for you to visualize. It's a nice way for you to visualize. This is taking a bit of time, but let me just show you a few examples of what you can do with embeddings first. We'll talk about chunking. Chunking it's easy to do chunking, but I'm going to show you a very simple naive chunking algorithm if you wanted to just do a very simple um, you know, fixed size chunking, right? Okay, so let's start with simple naive chunking. Okay, so let's start off with just doing I'll try to be fast because we run out of time. But let's start off with doing just simple fixed size chunking. Um, so it's not complex, it's very simple. Let's assume you have, let's just do a function. So a simple function, chunk text, right? The text that you want to chunk, um, then you specify the chunk size, which is means then you specify the overlap. So remember we talked about overlap. So remember when you chunk text, you're always going to get back a list um of string, which is a chunk. Okay. So um let's just start by saying well, this is some kind of, if you want to do some error checking to make sure that the overlap cannot be higher than chunk size, right? So you can even say, okay, chunk size, or overlap cannot be higher than overlap, cannot be larger. So just a little bit of validation, chunk size. Okay, another thing to do is chunk size must be greater than zero. So if chunk size is less than or equal to zero, I wouldn't even say zero. Like it doesn't even make sense for you to have a chunk size of zero, right? But that's okay. So all this validation, good practice to have validation. Now you create a simple chunks array, and then you now specify how many chunks you want to split it into. So it's very simple. For I in range of 0 to length of the text, right? And chunk size minus overlap. So why you are doing chunk size minus overlap is, let me make this steps, right? Step. So step here means um, you take the chunk size and then you take back the overlap. Um, but when you want to take the subset of the text, you're actually going to add back the the overlap, right? So um so you just loop through it, right? So you're essentially going to jump by the chunk size minus overlap, and then the chunk you take. This is basically taking a substring of the text that you're chunking from I at the particular position to the next position, which is the chunk size, right? Um, but you're always going to step over, the actual steps you're taking is the overlap. So this allows you to have some overlap. And then that chunk, which is a subset, you pass in, you add it into the list of chunks, and then you return the list of chunks. It's as simple as that. This is basic naive chunking. Now let's try a few examples, right? So try a few examples for chunking. So let's say I can take a really long paragraph. Um, so I'm just going to get a lorem ipsum generator here, and text equals that. So I will take this. Um, I'm going to take this. So this is a pretty long text. Just lorem ipsum. I'll paste it here. Okay. Um, I can check the length of the entire thing, right? So length of text. It has 4,410 characters. So I don't know the number of words. Um, Now we can do chunk size. So let's go with a simple chunk size. Chunks is let's say chunk size we want um let's just say maybe 20 words. Um in this case the chunk size is the tokens or the characters in this case, because this is basically characters, right? We are using we did not we did not convert the the text into words, or we are not counting words, we are counting characters. So let's assume we have with this 4410, let's assume we are using chunk size of maybe 200. So I would expect it to give me about 20 or so chunks, right? So we'll call on the chunk text function. Chunk size is, let's say 200. Overlap. So we say overlap maybe 10 to 20%. So I'll just take 10%, which is, or 15%, which is 30. Okay. So when you do that, I'll print the chunks so you can see. What is simple, you can see the chunks that we have here. And you see sometimes it chops it off. Here there's a comma, but here it chops it off. Oh, there's overlap, by the way. So you can see the overlap allows this to go back all the way to this point, right? But you also see that even though there's overlap, but this particular word has been split in the middle of the word itself. So this is just very basic stuff. Okay. Now there are more advanced chunking, and we're going to look at we've seen already how they work. We're going to when we get to lang chain, we're going to use lang chain to do a bit more with this. Now, yeah, so this is an embedding projector. Um, I was waiting to load. So you will see that there are different words here. I want to see if I can get um, different colors in. So this will take a bit of time. So come back to it. Now, let's do a bit of embedding. So to do embeddings, you will need to be in the, you need to get an embedding model. So let's go to Hugging Face. Hugging Face has um, lots of them. You could also do it from Open Router and Co. Right? There's so many places you can get. Um, so you go to models and then you go to embedding. You can actually see the different types of um, yeah, let's see. I want to do embedding. Or I could just search for it here. Okay, so this allow you to do a lot of stuff. But let's use um let's use the all mini because I think we already have a code sample where we can use the all mini, right, with sentence transformers. So we are going to just use that. So from sentence transformers, import sentence transformer. Okay. Um, Let me be sure that this is important. You can also do this. I'll also show how you can use an API call. The sentence transformer is going to download the models down here, but you could also use an API call. All right. Um, so we will use the sentence transformer. So the sentence transformer, why it's called sentence transformer is basically it's a transformer that has been trained obviously on sentences. So they do very well on embeddings. Okay. It's as simple as that. So you create a model of a sentence transformer and that's it. It's going to download a copy of the model weights and have them locally. And it should be very fast because embedding models are not as heavy as um, LLMs, as large language models. Now that we have this, right, let's try a bit of embeddings. Yeah, so embedding model is, well, embedding visualizer is a bit slow. I was trying to get a multicolor thing. Let me go back to PCA. The T-SNE is too. Let me now go to let me just go to it. Here, this is not working. No color map. Yeah, but this is kind of a visualization of an embedding space, even though this it's very clustered. So um, but these are all each point in this space is a word, right? And you see that words that are in the same space. Let's see if I can zoom in. You can actually see that words that are close together have similar meaning. Agreements, infrastructure, agricultural, bilateral. I don't know where these words came from, but um, this is kind of a visualization of embedding space. Probably not the best visualization, but it allows you to see words as meanings. Okay, let's go back to this. So I have a model that I have done. I can now do the embeddings. To do embedding with sentence transformer, you use model.encode. Just use model.encode. And then you specify the words that you want the embedding. So let's start with a simple word, artificial. If you run this, you're going to get a vector, right? So here is a vector. You can already see it is a list of lots of numbers. That's what it is. Typically, you don't even want to print the whole thing, okay? But it is a list of um, numbers. If you want to check the length, you find that it is it's 384. There are 384 numbers in it. So that's what it is. If you are looking at just the embedding itself, it doesn't make any sense. It's not something you can use, right? Not that it doesn't make any sense, but it won't make any meaning to you. But it makes meaning to the large language models. So but you could also put in multiple words. Artificial intelligence is now going to give you two vectors, right? And you could look at the shape of those two vectors. If you look at those two vectors, you'll see that, sorry, if you look at this response, you see that it is two. It is, okay, it's actually giving you the embedding of the two words as one. So it can give you the embedding of a whole sentence, a single word, and so on. Now, if you give it a list, it will give you the embedding of each of the words in the list. So here I have a list of two words. I've now separated them into two words, and I get two different vectors. You see it as two different vectors. So you see there are two of them now, and each of them has 384 elements. Right. Now, the other thing you can do, like I was saying, is you can do embedding for multiple. So not just for a single, but for multiple text. So this one that I had chunked, right? I can then take all of these chunks and then do embedding on it. So that's where it begins to get interesting. So you could do something like model dot chunks. I don't need to print out everything. We know it's going to be a list of numbers, but this is just to help you see. You can see we now have 26 of them, right? We now have 26 of them. Each is 384. If I were to print this out, you can see all of them actually. But now there are so many that it's shortening it. But you definitely will see that this is 384 length. This is the first one. This is the second one. This is the third one, and so on. And this is the last three. So now, where it becomes interesting is where you want to now do stuff like cosine similarity. Okay. Um, Cosine similarity. Okay. So for you to do cosine similarity, there are different libraries you can use for cosine similarity, right? But I don't want to go into the maths of it because um I want to do this so that you can see what cosine similarity um will do in terms of being able to see the meaning, right? There are many different approaches, right? Um, there is you can use sklearn. This is a Python library, right? Now, if you're using JavaScript, you may be asking, okay, how do I do this with JavaScript? But there are libraries everywhere, right? I'll show you examples of how to do this with um, you know, JavaScript. But let's just use this as a cosine similarity function that is in this sklearn library. In most cases, you are not going to do this because the vector database is going to handle all of these things for you. So you're not going to have to think about it, right? Right now, I'm kind of just doing a bit of first principles because I don't want to um, jump ahead. So I could do cosine similarity. So first of all, let's take the two words that we're talking about before, or the four words we're talking about before. So let's say words, just words alone. You have a word, a car, right? You have, I had four words, car, care, um, card, and automobile. So these are four words that I was using to kind of explain it. So we have these four words. We can now get the embeddings for the four words, right? So the embeddings would be the model, embedding model dot encode, and you specify the words. So we have embeddings for these four words. Okay, I can then print the embeddings. If I print the embeddings, you will see them. You really cannot tell anything by just looking at the numbers because the numbers are just decimal numbers. Um, but where it begins to get interesting for you as a person to see what happens, so when you start doing cosine similarity. So to do cosine similarity, right? Um, let's start with a simple one. Calculate the cosine similarity. By the way, the cosine similarity function allows you to compare a single, um, you know, a single embedding with multiple. But for now, um, let's just compare the, yeah, let's just compare the first words. Let's say the word that we want to compare is car, right? And the car, the embedding of car is embedding 0 because when you encode the words, the embeddings will also come in the same sequence as the words. So the first word is car, right? Word 0 is car, so embedding 0 is also the embedding for car. Alternatively, let me just be very, so let's say the car embedding is, let's just do it for the car only. um, car. Okay. So we have the embedding for the car, which is the meaning of the word car. Then we have the embeddings for these four words. And they're all there, right? If you print this, let's print it so that you can see the embeddings, like it's better to always print the shape. So let's just do the shape. Um, you can see it is four words, while the shape for car is just one because it's one word. Okay. Um, Now I want to do cosine similarity. So to do the cosine similarity, I am going to compare the uh, first one with the last one. Sorry, with this car. So I can do a cosine similarity of embeddings. Remember, embedding 0 is the first, which is a car itself. And let's see what we get. Okay, so it is now, if your data has a single feature array, so I have to reshape. Let's just do this. And this is a bit of machine learning stuff. So please pardon me. Reshape -1, -1 and 3, 8, 4. All right. This is an internal detail. So, all right, what this does is it is now comparing each word with the car embedding. So basically, remember the first word here is car. So I'm effectively comparing car with itself. And I'm comparing car with itself, right? These embeddings is all of them. The thing with all of these methods is that it allows you to do multiple things at once. So I'm effectively taking all of these forwards and the embeddings from them, and I'm now comparing the embeddings from them with the embeddings from this single word car. This is what I just did. And don't worry, you don't need to be doing this. This is more of a machine learning thing. But all of this magic is now hidden under the libraries that we'll use, particularly the vector store, pinecone, and so on. So we'll look at that when we come in on Friday. But what I just wanted to show you is this. When I compare car against itself, I get a cosine similarity of 1. That means exactly the same meaning. When I compare car against card, right, cosine similarity is 0.3. It's low, but it's not 0. So there's still a correlation, right? As long as there's a little correlation, and that correlation may be that, oh, okay, they have this similar spelling, or this one is just one character away from being. So you can see it's not entirely 0. That means there's a correlation. I now compare car against card, which is the second one. Let me bring these ones back here so that we can see. And you can see that when I compare car against card, I also have a value, right? This one, I have a value of 0.418. So it's not 0, so there's still a correlation, but it's a low value. It's below 5, below 0.5. Then automobile, you can now see automobile, right, is 0.8. So this is very high. So you can now see that cosine similarity is now telling you this word automobile is very close to car, which I was comparing it with. We can try a few other things, and I would recommend trying a lot of things. There are many different ways of basically doing this thing, but this is kind of giving us an idea. So when you are doing similarity search, there is also an algorithm. And again, you don't have to write all of this because the vector database handles all of this for us under the hood. What I just did here is like first principles based on machine learning ideas, right? So this is not AI for developers, this is more of machine learning stuff. But This is what is going on under the hood. So let's try maybe words that are opposite to let's try words that are opposite. So for example, let's try another set of words. Um, maybe king. Let's try king, queen, um, um, boy, right? Girl, and man and woman. Okay. So these are now the words. And I now want to compare it with, let's say we want to, yeah, so let's do embeddings for that one. Model dot encode words. Okay. So that gives me the embedding for those. Then the um the one I want to compare with, right? The let's say female, right? So female, I do the embedding for female, female. I now want to, I have to reshape this by the way, so that again 384, I think 384. So that I get it to the same shape. So I can now do the cosine similarity again of embeddings. This time is embeddings for these 6 words: king, queen, boy, girl, man, woman. Okay. So I'm going to do that and compare it, how similar it is with the female, which by the way, I've already reshaped it here. So I don't need to reshape it again. So let's compare and see. You now see that I picked female. So you find that the ones that are female will tend to have a high um, similarity score. And the ones that are male will have a low. So the king has a low score, 0.249. The queen has a low score too, but it's higher than the king because the queen is female. The boy has a low score, 0.8. But the girl has, you can see, has a very high score comparatively. The man has a low score as well, but the woman has a very high score. So you can see that cosine similarity kind of gives you meanings. So even when the words are not the same, or even the meanings are not exactly the same, but the meanings are similar. So let's try now with male, just to prove it. Male is model that encodes male. Then reshape minus 1384. Okay, then we'll now do a cosine similarity of these embeddings with the male this time around. And you see the difference. So you now see that the ones that are male will have a higher correlation. Okay. So here the king has a higher correlation than the queen, even though the king's correlation is still low. It's interesting how these two have the same, maybe I made a mistake here, but yeah, so boy and girl now have the same. That's strange. And then that's interesting. So well, maybe the model has not been trained enough on this data, right? So, but that is what embeddings do. The better the model, the better your similarity scores that you will get. So I'll end it at this point. Are there any questions?